In this video, I'm explaining you how the cyclic redundancy check method for bit error detection works. At first, some preparation is needed. In the calculations, we use the modulo 2 arithmetic, or you can also say the exclusive OR function. So if you calculate 1 plus 1, the binary result is not 1, 0, but just 0. As we will see later on, this is in particular beneficial for implementing the CRC method in hardware. Then another way of representing a bit sequence is needed, which is called the polynomial representation. You can imagine a variable x and represent each bit as a power of x. If the bit is a 1, then the power of x is there, otherwise it is left out. All calculations can also be done without using polynomials, but it is then much more error-prone for humans. In the method, we now represent two bit sequences as polynomials. The message to be transferred is represented as message polynomial m of x. Then there is the so-called generator polynomial g of x, which is the same for all messages and is known to sender and receiver. M of x and g of x are input for the CRC generator, which provides the transfer polynomial t of x. The calculation is done as follows. M of x is multiplied by x power r minus 1. R is the number of terms that the generator polynomial has. It's a representation as bits. It means that if g of x consists of 4 bits, then you add 3 zeros to the message. Afterwards, a division by g of x is done. This division gives a quotient and a remainder. After two transformations, you find the definition of t of x. It is an addition of the remainder to the m of x multiplied by x power r minus 1. The t of x has been defined in a way that it can be divided by g of x without remainder. This is the basis of the test, which is carried out on the receiver side. In my view, it is easier to understand the method based on an example, which you can find on this slide. Here we have a message polynomial and a generator polynomial. Since the generator polynomial has 3 bits, 2 bits are added to the message polynomial. Then the division is carried out. You can ignore the quotient because the important result of the division is the remainder. The remainder is added to the multiplied message polynomial. Seeing it in the bit representation, the remainder replaces the 2 bits which had been added before. On the receiver side, you later receive a t of x which may have been corrupted. You do again a division, that is, now you divide the received t of x by g of x. If the remainder is 0, then you assume that everything is fine. If the remainder is not 0, then there is at least 1 bit error. However, you cannot locate the bit error, so that at the end a retransmission is necessary. This slide should give you a short glimpse that the implementation of the method in hardware is not as complicated as you may guess. The letters A, B, C, D, and E represent shift registers. They can store a single bit, and in the next clock cycle they shift the stored bit to the next shift register. However, exclusive OR calculations are possible as well. So in general, the message traverses the shift registers starting from the right-hand side, and at the end, the shift registers contain the remainder. The last slide shows that the CRC method is actually very reliable. If 2 prerequisites on the generator polynomial are fulfilled, then the shown likelihood conditions hold. If there are longer error bursts, that is, sequences of bits affected by several errors, there is a very small likelihood that errors are not detected.